this section we're going to state and prove Heisenberg's uncertainty principle. This is a fundamental result in quantum theory. We begin then with the following proposition. Let A and B be self-adjoint operators, and we're going to write the commutator of A with B as I times C. We saw in the last video that C is then automatically a self-adjoint operator. Then for all real numbers S, and also for all normalized states psi, we have the following relations. So firstly, if we take A minus IS times B, and we take the adjoint of that, times, and then in brackets, A minus IS times B, then that operator is equal to A squared plus SC plus S squared B squared. Secondly, here we have the square norm of a state on the left-hand side, and that state is, well, in brackets, A minus ISB acting on psi, and that's equal to the expected value of A squared plus S times the expected value of C plus S squared times the expected value of B squared. And finally, in 3, this is the key result. So the expected value of A squared times the expected value of B squared is greater than or equal to 1/4 times the expected value of C all squared. Moreover, we get equality in this last inequality if and only if there's some real S subscript 0 such that A minus I S0B acting on some state psi is equal to 0. The proof of this is just really direct calculation. So let's start with the first relation. On the left-hand side, I've got A minus ISB adjoint, and then times A minus ISB. And in order to take the adjoint here, notice that A and B are both self-adjoint, S is real, and when we take the adjoint of I, we get minus I. So we can write this as A plus ISB times, and then brackets, A minus ISB. And then we can expand out this composition of operators. So we get A squared minus IS, and then in brackets, AB minus BA plus S squared times B squared. So notice in the line above, we have a difference of squares, and we don't simply get A squared plus S squared B squared, precisely because the operators A and B don't commute with each other. So notice that we have the commutator of A and B as the middle term here. On the other hand, that commutator was defined as I times C. So in the line below, that's equal to A squared plus SC plus S squared B squared. And that's exactly the relation that we wanted to prove. For the next one, on the left-hand side here, we've got the square norm of a state, and that state is A minus ISB acting on psi. The square norm of a state, though, is just the inner product of the state with itself. That's the definition. So I've written that here on the right-hand side. And then I'm going to take the operator here, A minus ISB, onto the right-hand side, where it will become the adjoint operator. So that's what I've done on the next line. So we have psi inner producted with A minus ISB adjoint, and then A minus ISB all acting on psi. But then this composition of operators here is precisely what we computed in the step above. So I can replace that by A squared plus SC plus S squared B squared. But then by definition, this is the expected value of this operator in the middle here. Using linearity of expectation, I can then write that as expectation of A squared plus S times the expected value of C plus S squared times the expected value of B squared. And that's exactly the relation that we wanted to prove. Notice here on the left-hand side, we have a square norm, and that's greater than or equal to 0. We then deduce that the expression on the right-hand side is also greater than or equal to 0. So we can write that on the next slide here. That implies that the expected value of A squared plus S times the expected value of C plus S squared times the expected value of B squared is greater than or equal to 0. this is a quadratic expression in S. And to say that this is greater than or equal to 0 means that the quadratic must have discriminant. So remember that the discriminant is just b squared minus 4ac in the usual notation for a quadratic equation. So the discriminant must be less than or equal to 0. That condition is that the expected value of c, all squared, minus 4 times the expected value of a squared times the expected value of b squared is less than or equal to 0. If you rearrange that inequality, you precisely get the inequality that we stated in the proposition. Finally, we just have the case where we have equality in this inequality. In that case, notice that the quadratic expression that we started with up here has a repeated real root. So I'm going to call that real root s equal to s subscript 0. Now we've got a quadratic equation, so 0 is equal to the expected value of a squared plus s0 expected value of c plus s0 squared, the expected value of b squared. But in the previous part of the proposition, we proved that this was the square norm of this state here in the brackets. So we've got a minus I s0b times psi. We therefore see that s0 is a root of the quadratic if and only if this square norm is equal to 0, but the square norm of a state is equal to 0 if and only if the state is 0. So we see that a minus I s0b acting on psi is equal to 0. Okay, so that proves the proposition, and a corollary is Heisenberg's uncertainty principle. So I'll state the uncertainty principle here, and then we'll see how it's proven from the proposition on the next slide. It states that for a normalized state psi, we have the following inequality. So the dispersion of x times the dispersion of p in the state psi is greater than or equal to a half h bar. Moreover, equality holds in this inequality if and only if the state psi has a Gaussian wave function. So that is, we can write psi of x as an exponential, and then in brackets here we've got a constant 1 over 2 s0h bar, and then that's times x minus mu all squared, plus a constant gamma. So mu and gamma here are complex constants, and then notice that this will be a normalizable wave function precisely when s0 here is less than 0. We then get a Gaussian integral, and that will be convergent. In this case with equality, we say that psi describes a minimum uncertainty state. Okay, so we can prove this from the proposition as follows. We take the operator A in the proposition and write that as x, the position operator, minus the expected value of x times the identity operator. And then similarly, we write B as the momentum operator, minus the expected value of the momentum operator times the identity operator. Notice that the expected value of A and the expected value of B are both equal to 0 by construction. Next, we can use linearity of the commutator to compute the commutator of A with B. So if we look at this, we'll get a commutator of x with P from the first term. We'll also get a commutator of x with, and then minus the expected value of P times the identity operator. On the other hand, the identity operator commutes with all operators. So this second term I've written here will immediately be 0. And then similarly, we get minus the expected value of x times the identity operator commutated with B, but that's equal to 0. So the commutator of A with B is equal to the commutator of x with P, and that's equal to IH bar times the identity operator. That was the canonical commutation relation. Remember then that C was defined as minus I times the commutator of A with B, and from the line above we can see that that's just H bar times the identity operator. Finally, the expected value of A squared is by definition just the dispersion of x squared, and similarly the expected value of b squared is just the dispersion of p squared. And since the expected value of c is h bar, this inequality in the proposition will give us the Heisenberg uncertainty principle. So specifically here we'll get the dispersion of x all squared times the dispersion of p all squared is greater than or equal to 1/4 times h bar squared. If you now take the square root of both sides, that's precisely the Heisenberg uncertainty principle that we read before. Let's look at the case with equality. The proposition, remember, told us that you get equality in that inequality precisely when there's a real number S0 for which A minus I S0B acting on a state psi is equal to 0. So it's convenient here to set mu to be the expected value of x minus I S0 times the expected value of p. Those are the terms with expectation values in them. And then A and B are written in terms of the position operator and the momentum operator. And we're going to substitute the momentum operator for minus I h bar d by dx. So when we have equality, we have that 0 is equal to A minus I S0B acting on psi. And then we substitute the explicit expressions for the position and momentum operator. So for A, we have the position operator x, then we have minus I S0, and then B gives us a momentum operator term, minus I h bar d by dx, and then we have minus this term mu with the expectation value terms in it. All of that operator then acts on a wave function psi. If you look at this equation, you can see it's a first-order differential equation for the wave function psi. If you rearrange it, putting the derivative of psi with respect to x on the left-hand side, well, that's equal to 1 over S0 h bar, and then a linear term x minus mu, all times psi. That's a first-order linear differential equation for psi, and we can immediately integrate it to get that the log of psi is equal to 1 over 2 S0 h bar times a quadratic term, x minus mu squared, from integrating the linear term, and then there'll be plus an integration constant gamma. If you exponentiate this expression, you precisely get the Gaussian wave function that we wrote in the statements of the Heisenberg uncertainty principle. Okay, so that's a formal statement and proof of the Heisenberg uncertainty principle. Let's make some remarks, though, on what it actually means physically. Firstly, note that the Heisenberg uncertainty principle follows directly from the canonical commutation relation between the position and momentum operator. In fact, really that's all that we use to derive it. Next, note that the more precisely that the position of a particle is known, by definition, the smaller value of the dispersion of the position operator x in that state. On the other hand, as we decrease the dispersion of x, the dispersion in p, the momentum, must correspondingly increase so that the Heisenberg uncertainty principle is obeyed. So remember, that states that the product of the dispersion of x with the dispersion of p is bounded below by a half h bar. So the more precisely that we know the position of the particle, the smaller the dispersion in x, but then correspondingly the larger the dispersion in p, and so the momentum is then known with less precision. In other words, position and momentum cannot be simultaneously measured to arbitrary accuracy in quantum theory. This is very different from classical mechanics. In fact, usually for Newton's second law, you would give as an initial condition the position of the particle and also its momentum. But in quantum theory, you can't simultaneously measure position and momentum at some given time to arbitrary precision. Notice that this says nothing about the way in which you go about measuring position and momentum. You might imagine that when you try to measure the position of the particle, you're going to disturb its momentum in the process. Or correspondingly, if you try to measure the particle's momentum, you'll alter its trajectory and therefore alter its position. Both of those statements are true, but the Heisenberg uncertainty principle is a fundamental principle that says that no matter how you do the measurement of position and momentum, you can't know them to arbitrary accuracy. This is also why position and momentum eigenstates don't exist as genuine normalizable quantum states. So we mentioned this earlier in the course, and there's also a starred subsection of the lecture notes that discuss that in a little bit more detail. Let's look at the relation of this, though, to the Heisenberg uncertainty principle. Suppose that psi is a state with definite position. That means that the dispersion of the position operator x in that state is equal to 0. That was a proposition that we proved earlier. If psi is in an eigenstate of the position operator, then the dispersion of the position operator is 0 in that state. On the other hand, the Heisenberg uncertainty principle says that the dispersion of x times the dispersion of p is bounded below by a positive constant. So formally at least, if the dispersion of x is 0, then the dispersion of p must be infinite. That is, the momentum in such a state is completely uncertain. There are similar comments for momentum eigenstates. So we met the plane wave right at the beginning of this course, e to the I px divided by an h bar, and that's an eigenstate of the momentum operator p. That is, if we take minus I h bar d by dx and act on this plane wave, we precisely get p, the momentum, times the plane wave. We also commented earlier that the absolute value of this plane wave solution is equal to 1. In particular, it's a constant, and because it's constant, this function is not normalizable over the whole of space. In fact, the absolute value of the wave function squared being constant means that that describes a uniform distribution for the position of the particle. In other words, the particle is then equally likely to be found anywhere. That is, if you knew the momentum of a particle exactly, then its position is completely uncertain. So then you're equally likely to find that particle in your lab where you thought it was, as you are, say, down the back of your sofa, under Donald Trump's hairpiece, or indeed in the middle of the sun. We've seen an example of a minimum uncertainty state already in the course. So the Heisenberg uncertainty principle tells us that if the dispersion of x times the dispersion of p is equal to a half h bar, so we have equality in the inequality that we had earlier, then psi is described by a Gaussian wave function. But we've seen a Gaussian wave function already, namely the ground state of the harmonic oscillator. Remember that that was given by psi subscript 0 of x, and that's equal to a0, a constant, times e to the minus m omega x squared divided by 2h bar. Here omega is equal to the angular frequency of the harmonic oscillator. Finally, there's a generalization of the Heisenberg uncertainty principle that's usually called the generalized uncertainty principle. It says that if you have any two self-adjoint operators, A1 and A2, then for any normalized quantum state psi, we have the following inequality. So the dispersion of A1 times the dispersion of A2 is greater than or equal to a half times the absolute value of the expected value of minus I times the commutator of A1 with A2. The proof of this is almost identical to the proof of the Heisenberg uncertainty principle that we gave earlier. You set A to be equal to A1 minus the expected value of A1 times the identity operator, with a similar expression for B in terms of A2 into the proposition that we proved right at the start of this video. If you do that, it's straightforward to derive this inequality using the same method that we saw for the Heisenberg uncertainty principle, and there are some more details in the printed notes. What this says then is that if you have two operators, A1 and A2, that do not commute, then the right-hand side of this inequality is some positive number. That then means that the dispersion of A1 times the dispersion of A2 is bounded below by a positive constant. And in particular, you cannot measure A1 and A2 to arbitrary accuracy.